Okay, so today's video is to take you through how to calculate the pH in an acid-base titration. So calculate the pH of the analyte solution throughout the entire process of the titration. Okay, so this is 5-4 on your visible learning, and this lesson will show you, kind of walk you through how to do one of the scenarios on your 5-4 Schoology assessment. Okay, so today we're going to talk about if I have a weak acid in my flask and I'm titrating it with strong base, how could we calculate the pH throughout the titration? And then the next video eventually will be, I have a weak base in my flask and I'm slowly adding strong acid. How do we calculate the pH throughout that titration? Okay. But before you move on to this video, understand that you should understand what a titration is. Remember, we reviewed that back in unit 2. So if we look, remember these notes, right? So what we're going to try to do is we're going to visualize that we have, in this lesson, we're going to talk about, we have a weak acid in our flask initially, and we're slowly adding sodium hydroxide or a strong base to it. And what we're kind of imagining is we have a pH meter in this flask, and it's measuring the pH throughout the titration. So, after I add a few milliliters of the NaOH, what's the pH? Then I add a little bit more. What's the pH in the flask? That's what we want to be able to do. Okay. Another thing to understand is being able to calculate the pH throughout a titration is really not the goal of a titration. A titration is you don't know the molarity of what's in the flask, and you're doing a titration to figure out what that concentration is, right? That's the whole point of any titration, whether it be acid or base or oxidation reduction, right? So understand that this type of problem that we're doing here is just an exercise in understanding all of the concepts, all the acid-base concepts. So in this, we're going to be doing a titration with an acid we already know the molarity of. So we know the molarity of the acid that we're starting out with. We know the volume of the acid that we're starting out with. We know the molarity of the sodium hydroxide. And what we want to do is be able to, if I add this many milliliters of sodium hydroxide, what's going to be the pH? If I add, add a little bit more, what's going to be the pH? Okay. So again, this is just an exercise. So the type of problem we're going to do is we're going to do this type of problem in class to practice, but this is essentially the setup, right? You're going to have a weak acid. So notice we have a weak acid in our flask, and we're given the volume that we start out with. We're given the Ka of the weak acid, acetic acid, and we're slowly adding sodium hydroxide. And we want to be able to calculate the pH in the flask after zero, before the start of the titration, when we haven't added any sodium hydroxide, after 5 milliliters, after 10, after 15, after 20 milliliters added. We want to be able to calculate the pH in the flask after, this many milliliters of NaOH solution have been added. And so notice we are given the molarity of the acid. We're given the initial volume of the acid in the flask. We're given the molarity of the sodium hydroxide. So again, this isn't really the point of a titration. It's just, if you understand acid-base chemistry really well, you would be able to predict or calculate the pHs at each of these volumes of sodium hydroxide added, right? That's our whole goal, all right? So again, before you start, make sure you watch the video on titration curves that I did. These are the lesson notes that I've already gone over. Make sure you kind of watch that video because that'll help you out understanding the language I'm using and the stuff we're doing throughout this scenario. Okay, so here we go. All right, so we have a weak acid, HCN. We're given its Ka, 5.3 times 10 to the negative 7. We're going to titrate it with sodium hydroxide. So again, if we understand our setup, I got the HCN in the flask, and I'm slowly adding hydroxide. Remember, I never care about the sodium, right? Okay. So the reaction that's going on is, and this reaction essentially goes to completion. So every hydroxide I add will take out one of the HCN molecules and produce water and cyanide. And what we have to recognize is cyanide is the conjugate base of HCN, hydrocyanic acid. Okay? So here's the scenario. 20 milliliters of the 0.15 molar HCN. So again, if we go back to the setup, we have HCN in the flask, the molarity is 0.15 moles per liter, and we're starting out with 20 milliliters in there, okay? Oops, all right. And we're slowly adding this molarity, 0.20 moles per liter of sodium hydroxide, okay? And we want to calculate the pH in the flask after these volumes of NaOH have been added. So after 0 milliliters, so before the titration, after we add 5 milliliters, after 7.5, after 10, after 15, and after 20, okay? All right. So the first thing I want to do, in this type of problem is figure out what volume of sodium hydroxide it takes to reach the equivalence point. And remember, so the equivalence point equals moles of that is the point where moles of the HCN equals moles of the hydroxide. And at the equivalence point, if moles of this equal moles of this, they completely take each other out. So at the equivalence point, you don't have any of this and you don't have any of that. All you have is the cyanide. Yes, you have H2O, and yes, you have sodium ions, but in terms of pH, we only care about the cyanide. So let's figure out the equivalence point, and that's a simple MAVA equals MBVB calculation. So the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So we solve for the volume of the base required. So 15 milliliters is going to be 15 milliliters of sodium hydroxide added is going to be my equivalence point. So boom, you know that right there, right? These are the different volumes of NaOH added that we want to calculate the pH in the flask of. Well, that's the equivalence point. Right there, boom, okay? So we know the OH minus and the HCN have canceled each other out at 15 milliliters of NaOH added. So so at that point, to calculate the pH at the equivalence point, all we have is a weak base in the flask. So we're gonna do a KB shortcut there, all right? The next thing I'm gonna do is I'm gonna half the molarity, or sorry, not the molarity, the volume of sodium hydroxide at the equivalence point, because that's going to give me the half equivalence point. So 15 milliliters is our equivalence point, divided by 2, 7.5. So our half equivalence point is 7.5. And remember, in a titration, the half equivalence point is where pH equals pKa. So that's going to be the easiest one to calculate overall. So again, if we look at all of our molarities, that's the equivalence point. So at this equivalence point, or not at the half equivalence point, 7.5 milliliters, all I have to do is take the negative log of the Ka, which I was given, okay? And the reason why this is true is because at the half equivalence point, the moles of HCN in the flask is going to equal the moles of CN minus, so you have a buffer system, and you have equal amounts of your buffer components, so pH equals pKa, all right? So let's map out the problem. Now that we know that this right here, that's the equivalence point, okay? And that's the half equivalence point. Let's map everything out. All right. So before the reaction starts, before we add any sodium hydroxide, just a Ka shortcut. All right. We have a weak acid in the flask. We know the Ka and we know the molarity. Ka shortcut. That's how I'm going to calculate the pH. Okay. Anywhere between the start of the titration and the equivalence point, we're in the buffer zone. So 5 milliliters, 7.5 milliliters, and 10 milliliters added is in the buffer region. So I'm using the Henderson-Hasselbalch, but remember our little shortcut for the midpoint of the buffer region, the half equivalence point, pH equals pKa. But again, I get that from using the Henderson-Hasselbalch equation because it's pH equals pKa plus the log of 1, and the log of 1 is 0, so pH equals pKa. So I'm using my Henderson-Hasselbalch for these, okay? At the equivalence point, it flips. So before the start, it's a Ka shortcut. That means at the equivalence point, it's going to be a Kb shortcut because what's in the flask? A weak base now. Okay. The reason why it's buffer here is because we have both HCN and CN minus in the flask before we reach the equivalence point. But at the equivalence point, we've taken out all of the HCN and we're left with just cyanide, a weak base. So we're just going to do a Kb shortcut. And then at 20 milliliters added, we're beyond the equivalence point. So that means, think about it, we've added hydroxide, but we don't have any HCN in the flask for it to react with. So the hydroxide doesn't react with anything, so the hydroxide remains in the flask. So all you have to do for this is just figure out what the new molarity of hydroxide is in the flask. Negative log of that is the POH, and then 14 minus is the pH, right? Okay. So that's the map, and now we just got to execute, right? We got our plan, let's just go execute the plan. So the values we got to remember, this was the molarity of HCN, and we had 20 milliliters of it, right? This is the molarity of sodium hydroxide. We have our Ka, so do your Kb calculation real quick. So Kw divided by Ka gives me the Kb for cyanide, because I'm going to need that for at the equivalence point, right? And then also, I'm going to be using the Henderson-Hasselbalch equation, so I might as well calculate the pKa real quick. So if I take the negative log of that, that's where that 6.28 comes from, okay? So let's go. 0 milliliters added. So Ka shortcut, Ka equals x squared over 0.15, which is the initial molarity of HCN minus x. Okay, we 5% rule the x, so we get Ka equals x squared over 0.15. Okay, cross multiply, we solve for x. Remember, in this shortcut, x represents the hydronium concentration. And so if we take the negative log of that, we get our pH. So the answer for 0 milliliters of NaOH added to this question is 3.55. That makes sense. We got an acid in the flask, so we should have an acidic pH, right? Okay, so let's do 5 milliliters added. So we're in the buffer region. So this is how I suggest you do it. Make a BCA chart like you would in a buffer attack question. But in this case, we're not starting out with a buffer. So our before is we just have moles of HCN, right? We don't have any CN minus, okay? But what's going to happen as I add OH to HCN, it's going to take out the HCN and produce CN minus, right? So we're going to make our BCA chart. I do liters times molarity. So remember, we started with, what, 20 milliliters of our HCN, and it was 0.15 molar. So 0.02 liters times molarity gives me moles. So that's how many moles of HCN I have in my flask to begin with. I have 0 cyanide. Remember, the change is the amount of NaOH you added. So remember, the molarity of NaOH was 0.2 molar, so, and we added 5 milliliters, so 0.005 liters times 0.2 is where we got moles of hydroxide. So I'm going to lose that many moles of HCN, I'm going to gain that many moles of cyanide, and we do our math, and that's our new amounts. Okay, now, understand that our new volume at this point is 25 milliliters. We don't need to calculate the molarities of these, but if we needed to, we would be dividing by 0.025 because we started with 20 milliliters of the HCN in the flask, and at this point we've added 5 milliliters of NaOH, so our new volume is 25. So I just made a side note there for us to truly understand what's going on during this titration, right? So now all we have to do is plug that into the Henderson-Hasselbalch. So we say pH equals pKa, and we already solved for the pKa, 6.28. And it would be plus the log. Remember, it would be base over acid, so cyanide over HCN, so 0.01 over 0.002. And we get our pH. And it should make sense that the pH is lower than the pKa because we have more of the acid component of our buffer, all right? So that's our answer for after 5 milliliters added, okay? 7.5 will take our shortcut because we know we would have equal amounts of HCN and cyanide, so pH equals pKa. All right, so let's go to 10 milliliters added. 10 milliliters added, we're still in the buffer zone because we still haven't reached the equivalence point. Remember, we established the equivalence point at 15 milliliters. So now what we're gonna do is do another BCA chart. Same numbers, we start out, before the titration started, this is how many moles of HCN we had, and this is how many moles of cyanide we had, right? But now the change is this many liters, 0.01 times the molarity of sodium hydroxide, 0.2, So we're going to lose that many moles of HCN. We're going to gain that many moles of cyanide. And so after, everything's settled, this is how much HCN I have, and this is how much cyanide I have. So now we know, since we have more of the base component, our pH is going to be slightly above the pKa. So we would plug into our Henderson-Hasselbalch. And again, just note, the new volume at this point is 30 milliliters, because again, we started with 20, we added 10, so we got 30 milliliters. Just in case you wanted to calculate those new molarities, we'd have to divide by 0.03, okay? All right, but we can plug in moles into the Henderson-Hasselbalch, so we go ahead and do that, and we get our new pH. So after 10 milliliters, it's 6.58, okay? And after 10 milliliters of sodium hydroxide added, our pH in the flask is 6.58, all right? All right, so now 15 milliliters. Remember, we've established this is the equivalence point. So what's in our flask? Well, we don't have any more HCN. It's all been taken out. And we don't have any hydroxide because that's all been taken out. They've taken each other out, okay? So what is in the flask that affects pH? Well, we know sodium ions are just spectator ions. They're in there, but they're not going to change the pH, right? And we got water molecules being produced as well, but that's not going to affect the pH. So what is going to affect the pH? The cyanide. So we're going to do a KB shortcut. But here is kind of the tricky part. We got to figure out the molarity of cyanide. We know the KB. We did KW divided by KA to get the KB. So we got the KB. But we need that. That's the molarity of cyanide, right? We need that. So we need moles per liter, right? Well, the new volume at this point of the titration is our 20 milliliters that we started with of HCN plus the 15 milliliters of the NaOH we've added to this point. So our overall volume is 35 milliliters. So we know our volume, 0.035 liters. We just got to figure out moles of cyanide. Well, understand that moles of cyanide will equal the moles of hydroxide you've added, or you could say all of the hydrocyanic acid, all the HCN, has become cyanide. So the moles of HCN you started with equals the moles of cyanide you finished with. However you think about it, you just got to know how to calculate that number of moles, all right? So 0.003 moles of cyanide in our flask. The volume is 0.035 liters. So we get our molarity of cyanide. So we'll plug that in there. We'll plug our KB in and we'll solve for X, all right? So we take our KB, 1.9 times 10 to the negative 8 equals X squared over 0.086 minus X. We're going to 5% rule the X. So we get that. We solve for X. Understand, this is a KB shortcut. What does X represent in a KB shortcut? It represents the molarity of hydroxide. So we got our molarity of hydroxide. If I take the negative log of that, that is not the pH, that's the POH. So I'm going to negative log this, but then I'm going to subtract from 14 to get our pH. So our pH equals 9.61. And we should expect a basic pH because we're taking a weak acid and we're titrating it by a strong base. And whenever you do that, the pH at the equivalence point is above 7. And the reason that is because at the equivalence point, all you have is a weak base in your flask. Okay, so there's our pH. Okay, so now we'll go 20 milliliters added. Okay, so now we're beyond the equivalence point. So anytime you're beyond the equivalence point, all you have to do is figure out how many moles of hydroxide you have in the flask, divide it by the volume. That'll be the molarity of hydroxide, negative log, POH, subtract from 14, pH. Okay, so what's in the flask at this point? Well, we got sodium ions, that's neutral. We got cyanide, that's a base, but it's a weak base. But we got a bunch of hydroxide, strong base. So the strong base trumps everything. So we just go with, let's just figure out the molarity of hydroxide, negative log that, 14 minus, that's going to be our pH, okay? So we have to know how much hydroxide we have. So we have to know how much excess moles of hydroxide we added. So remember, we started with 0.003 moles of HCN in our flask. 20 milliliters of the NaOH added means we've added 0.004 moles of OH minus. But that's not how much we have in the flask because 0.003 moles of that will be taken out by the HCN. So what's going to be left over? 0.001 moles of hydroxide are left over. Our new volume is 40 milliliters, right? We started with 20 milliliters of the acid. We added 20 milliliters of the base. Our new volume is 40 milliliters, so 0.04 liters. So we get our new molarity of hydroxide. The negative log of that is the POH. 14 minus, that is the pH. So we get our pH. So in summary, here's kind of a chart, milliliters of NaOH added, and the pH in our flask. Okay? And then let's go ahead and, make a pH, titration curve out of that. So let's graph this, pH on the Y, and milliliters of NaOH added on the X, and we get our kind of titration curve here. So let me make it a little smaller so you can see it. Okay, again, I'm just sketching this. This is really, obviously I didn't use a ruler to make sure all this stuff was even, but notice we get our classic pH titration curve, weak acid, strong base titration curve, because, right, we get that initial jump towards the pKa, right? We started way down here because all we had was a weak acid, but then we have a buffer system, and that buffer system wants to get close to that pKa, so you get that initial spike towards the pKa, then you get your buffering, and then you get that big old spike as we slowly slide away from the buffer region and make it towards the equivalence point, and then it flattens out as we go beyond the equivalence point, okay? All right, so again, that was calculating the pH throughout an acid-base titration. This was weak acid titrated by strong base, all right? So I'll do another lesson sometime, hopefully I'll post it sometime next week, early, where it'll be the opposite, where you have a weak base in the flask and you're slowly adding strong acid to it. It's basically the same idea, but because we're always measuring pH in titration curves and not pOH, it can be a little confusing, because if it's pH, if it's a pH titration curve, at the half equivalence point, pH equals pKa of the conjugate acid of the weak base you're titrating. So that's where it can get a little confusing. But other than that, it's the same thing we just did. Just it'll be flipped. So if you think about it, in this scenario, before the titration, we did a weak acid shortcut. At the equivalence point, we did a weak base shortcut. So what's going to happen when we reverse it and do weak acid in the flask and slowly add strong acid? Well, before the titration starts, it'll be a weak base shortcut, a KB shortcut. At the equivalence point, it'll be a Ka shortcut. And then, but everything else holds true. Before the equivalence point, you got your buffer region, so Henderson-Hasselbalch. And then beyond the equivalence point, it's just excess H plus now. Figure out your molarity of excess H plus that you added. Negative log of that will be the pH, okay? So that's it in a nutshell, but I'll do another example for you in a video next week, okay? But that should be more than enough information to get started on that 5-4 assessment. You should be working on all the titration stuff, so make sure you're working on the concept check. If you want to wait on that 5-4 assessment until we actually do some more examples of this in class, that's fine. But doing the titration dry lab, watching this video, you should have a good understanding of what to do. So go give it a try, all right? Have a great day. Thanks for watching. Like and subscribe.